The first practical example of normal stimulus and response for ICMP that I want to talk about is the one that I think most people are probably familiar with, and that's the concept of an echo request and response. Now, an echo request and response is often referred to as a ping. That's not entirely proper because ping is actually just a tool that was written to generate echo requests and receive echo responses. But nonetheless, ping is a tool you're familiar with that allows you to test connectivity between two devices. So I can be on one device, Windows, Linux, what have you, type in ping 192.168.1.1, and it's going to send an ICMP echo request to that device. And if that device is up and listening and able to respond to ICMP messages, it will receive an ICMP echo request back with the same information that was sent over to it. So it's a pretty straightforward process. Ping is the tool that was written to facilitate that. Ping works cross-platform, right? We have ping on Windows, ping on Mac, ping on Linux. Pretty common thing, very easy to use. But I do want to demonstrate the normal stimulus and response, what that looks like both at a conceptual level, and we'll also look at some packets as well. Now, in this case, for our example, we'll say we have two systems, System A and System B. And System A, we want to make sure it can communicate with System B. There's a clear path there. To do that, I'm going to generate an ICMP Type 8 Code 0 message, which is an echo request or ping request if you want to use that terminology. It's going to pad that request with some data. It's different on a per operating system basis, and it's going to send that to System B. Now, if System B isn't up, it's just not going to respond, and System A will notice that it just doesn't get a response after a specific amount of time that the tool's configured to wait. Now, if System B is up and responsive and is able to accept and respond to this request, it's going to send a reply, which is an ICMP Type 0 Code 0 response, which is an echo or ping response. Now, you would think that the request is Type 8 Code 0, that the response would also be a Type 8 Code 1 maybe, or something similar to that. That would make sense, but unfortunately that's not the case here. They're actually completely different types. So the request is Type 8 Code 0, the response is Type 0 Code 0, and that will complete the ping or echo request and response process. So pretty straightforward conceptually here, but let's actually look at that at the packet level now. I've opened up the file ICMP_echo.pcap, and in this case you'll see we have 8 packets, and they're all echo requests and replies. We can see that very easily just by looking at the info column here. Now, in this case we have a source, which is 192.168.100.138, and a destination of 192.168.100.1. In this case, the source wants to communicate with the destination. It wants to ping it to see if it's alive, see it can communicate with it, see if there's a clear path there. So that's what we're observing. Now, we see a lot of the things we expect to see, right? We see Ethernet header, we see an IP header. I can expand that IP header. We see things we expect to see from what we learned about IP. We see the source and destination IP address and so on. We see that the embedded protocol is ICMP with the value of 1 here, so we know to expect an ICMP header next. Very straightforward. Now let's look at the ICMP header and expand that section. The most important part here is that we have a type and code specification. The type is 8, the code is 0, and Wireshark knows that that is an echo or ping request. That's what we would expect to see there. We have a checksum value associated with that, which it looks like we're evaluating here, and that's good. And then we have the variable portion of the packet. So in this case, our ping request has some identifiers and sequence numbers associated with it, and then it has a data portion. So I'm not going to focus too much on those identifiers and sequence numbers quite yet, but I do want to talk about this data portion. And if I click on that, you'll see we're looking at the hex bytes here, and down below it highlights that data, and we have an ASCII representation too. In this case, it's A, B, C, D, E, F, G, H, I, and so on. It's the alphabet. It's the alphabet followed by some additional letters followed by the text hi, H-I at the very end. Now, I mentioned earlier that with an echo request, some somewhat random data is padded to the end of the request when it's sent out. And the reason is the recipient is supposed to take that data and echo it back. It's supposed to send it back in the response. Now, this data isn't actually random at all. It's built into the operating system to pad this data. So this is, I believe this was generated from a Windows host, so this is the standard of what you would see with a Windows host. But it's going to vary based upon the version of Windows host Unix hosts are actually going to send a different request. So you can actually fingerprint and understand what the operating system source is, at least the architecture of the source, if you get an echo request from it just by looking at that padding, which is a pretty neat thing. Now, from an attacker perspective, keep in mind, you can pad anything in here. Anything I want can be put into this string and echoed. So it's not completely uncommon to see someone trying to send commands over an ICMP channel, because you can put any data in there, and most networks are configured to allow ICMP at least to a certain degree. So you can put whatever data you want in there, which is a good way to transmit data across certain links. One thing that's cool to do if you are intrusion detection system inclined is to look at all the operating systems on your network, build signatures that will detect any ICMP echo request padding data that does not match an operating system value you would expect. So anything that's odd or unexpected, detect that because it may be anomalous. That's a pretty cool way to go about that. So that's why I spent a little bit of time talking about the data portion of this packet here. Now, something I want you to pay attention to next is the identifier and sequence number fields. And you'll see I've got packet 1 highlighted. And I'm going to switch over to packet 2, and I want you to watch those fields, the identifier and sequence number fields. They didn't change. I'm on packet 2 now, which is the actual reply. So let's do that again. Here's packet 1. Here's packet 2. So a lot of things changed when I scrolled between those, but in this case, the identifier and sequence number didn't, and that's because that's how we pair replies to requests. That's how we know the reply is a response to a particular request, is through those numbers. Now you see BE and LE mentioned here, and that means Big Indian and Little Indian, and it just ways the order in which the numbers are represented. So in this case, you see Big Indian is 0500, Little Indian is 0005. So it's just the way the numbers are represented. In this case, dependent upon the architecture of the system that's processing it. So it's two representations of the same data, and that's perfectly okay. Now, with the reply, we see we have a type 0 code 0, which is what we expect. It's an echo or ping reply. Remember, in this case, our request was type 8 code 0. Our reply is type 0 code 0. And in this case, as I mentioned before, we see the same 32 bytes of data that were sent originally, but now we're sending them back. So the recipient has received the ping. It's now sending that back to the host, and it's echoing the same data back. And that's another way that the original host is going to some degree, validate that it's getting clear communication back. So if I scroll back up to the first packet, you'll see that 32 bytes of data remains the same as when I go to the second one. It bumps down a little bit because there's more information here, but nonetheless, it remains the same data. Now, Wireshark also gives us a couple of pieces of metadata that are interesting. So when I go to the reply, we see that it tells us the request is in frame 1, so it tells us where to find it. We can actually click this and it'll follow that link. And it also tells us the response time. So if you want to know what the response between the ping is, that's included as well. In this case, it was 0.776 milliseconds. So pretty snappy response time there. So there are a few more pings in here. There are 4 of them to be exact. So if you've ever run ping on Windows systems, you know it'll by default send 4 of those pings and try to get 4 replies back. So that's what we have here. We have 4 different pings, all sending the same data and getting it back. You notice the times change there. So in this case, this one was 5.178 milliseconds, 2.184 milliseconds, and so on. We see that listed down in this field here. So that information is stored and available for us as well. But this is an example of normal ICMP echo request and reply stimulus and response. Before we move on from ICMP echo request and reply, I want to talk about one more type of normal stimulus and response. And this is really in relation to firewalls or routers and going across the internet. So in this case, we have System A, and it wants to communicate with System B. And you see System A on the screen, you don't see System B, but let's just assume System B is somewhere out there on the internet, and there are several networks and several routers separating System A from that device. So we have to send our ICMP data out across the internet. Now, ICMP, as we know, relies upon IP. So all the same rules of IP-based communication apply, which means whenever we send a packet through a router, that router has to, it's natting, so it has to take the addresses, rewrite the addresses, recalculate checksums, deduct one from the TTL, all those different things. It modifies the packet a little bit, makes entries in its own tables, and then sends that packet on with the modified data. So the routers are interacting with that packet. So let's say in this case, we're sending an echo or ping request, type 8 code 0 towards our destination, and it gets to router A. Well, router A is friendly to ICMP data. It's configured to go ahead and send that along. So it's going to repackage it, recalculate that checksum, and send it along to router B. However, router B is actually not playing nicely with ICMP, and it's actually configured not to allow ICMP data through for whatever reason. In this case, it stops and does not transmit that packet any further. And in some cases, it might actually respond and say that there's a reason for that with another type of ICMP packet or something of that nature. But for the most part, generally, it's not going to respond at all. It's just going to drop the packet at the border, which means you'll never get a reply back. Now, the interesting thing is that doesn't mean system B out there on the internet is down. It doesn't even mean it's inaccessible. You may be able to communicate to it, through TCP, maybe port 80, it's a web server, port 53 on UDP, it's a DNS server. The system could very well be up, but a router along the path could be denying the ICMP traffic being forwarded along. So you don't see as much of that on the internet. A lot of times if the endpoint itself is pingable, if it's responding to ICMP data, most of the routers along the path generally will. But you do see this a lot in internal networks, is routers will be configured for security reasons not to forward ICMP data across the router boundaries. So keep that in mind. Just because you can't ping a device doesn't necessarily mean you can't communicate with it, first of all, and you may encounter multiple scenarios where when you're crossing multiple networks and different routers where ICMP packets just simply aren't being forwarded, and when that happens, you just simply won't see a response back. So ICMP echo requests, pings, they're a good way to test connectivity really quickly, but they don't necessarily mean there is no connectivity if they don't work, and that's an important thing to consider here when you think about the process of pinging something.